So, as I said in the class, next week I would like to spend more time on concrete mix design. So I decided that maybe it would be a good idea to have basically just this last part of cement, which is very descriptive, in a short video, which would kind of be considered as a makeup for one day I was sick, and can help us spend more time in the class on mixed design, where I see that the students need more help typically. In any rate, this is a simple, simple discussion, and if you need more information, please consult chapter 6 of the textbook. So what are admixtures? Admixtures are any ingredients which is not water, aggregates, cement or cementitious materials, and for example fiber reinforcement. And these materials could be added before or during mixing, and typically we do that to give the concrete some exotic properties. So for example, you may want to add admixtures to fresh concrete to decrease water content, increase workability, that means ease of placement and finishing, to delay or accelerate the setting, intervene in the process of segregation, etc. And you may also want to influence the properties of hardened concrete, for example, to help corrosion resistance or abrasion resistance, which is damage due to loading, if you remember. Damage due to loading. You may want to reduce shrinkage cracking, or even just to add a color to concrete. So what we discuss here are basically a few types of admixtures. Again, more information, chapter 6 in the class. One we have already talked about, air entraining agents, and then we talk about water reducers, retarders, and accelerators. We need air entrainment for increasing the resistance against freezing and thawing damage. We talked about this before, so you add entraining agent, which is kind of like dish liquid, and this creates tiny bubbles distributed all over the concrete. So if the concrete is subjected to cycles and freeze and thaw, then the water has a place to escape to. So when it increases volume due to freezing, then it doesn't basically crush the surrounding concrete and creates this kind of scaling. So it is being used for almost all concrete which is in cold climate, and it could decrease the strength because you're adding to air void content, and normally you try to compensate this by lowering water to cement ratio. So you lose a little bit of a strength, but you try to decrease the amount of water to compensate for it. As you can see, if you want to compare an air entrained concrete versus non-air entrained, then you see that if you compare the strengths, for example, at 28 days, basically the strength is lower for air entrained because of this excessive extra air voids. But we try normally to compensate it, because you see that if you lower the water to cement ratio, you can have higher strengths. So in the long run, if you have freeze-thaw problem, this is still beneficial. So the next one are water reducers. So water reducers, they increase the workability of concrete without changing the water to cement ratio. So there is a test called slump test. You may have seen it in C337 or will see it. And here you basically use a cone and fill it with fresh concrete, and then you remove the cone, and then you measure how much the concrete actually drops. The details are in these ASTM standards. Now, if you use water reducer, it basically increases the slump, and the way it does that is that the cement particles, they develop electrostatic charge on their surface during grinding, for example. So they tend to flocculate, cluster together, as you see here at A. So a molecule of water reducer looks like this. On one side it has negative positive charge, and the other side it's negative or positive. It comes and attaches itself to a cement particle, and then if it is attaching all over a cement particle, let's say if you had a few more attached here, then the cement particle becomes negative, and the negative charges, they actually are repulsive, so then the grains get separated, so comparing C to A, and that makes the concrete, the cement particles more mobile and increases workability. So if you want to compare when you have no water reducer compared to normal water reducer, here you see that the slump has increased. So when you remove the cone, it comes down a little bit more. And then if you are using even more water reducer without really adding more water and changing water to cement ratio, you are going to have even more slump. And there is a class of water reducers which are called Superplasticizers. So this is extreme high range water reducers, and this is when you need a really good flow, and you add that, and you get very high slump. And the important thing here is that you do not change the water to cement ratio, so you don't affect the strengths, because you know that water to cement ratio, the higher it is, the lower is the strength. So that's why you don't want to do that, but you want to have the kind of workability associated with higher water to cement ratio without having the negative effect of lower strengths. So we talked about superplasticizers. They can increase the slump up to even 9 inches, and then basically you don't really, they are called water reducers because to achieve the same increase in a slump, if you just wanted to add water, you would have to add 30% more water, which would mean much lower strengths. This typically doesn't last for long, so you need to add it at the job site and basically do whatever you need to do in terms of placement very fast, because after a while it's not affecting, it's not there anymore, so everything goes back to it was before. Another class of admixtures are retarders. These are delaying or retarding the initial set. Why this is useful? If you have a job in a hot climate, and if you are working on a massive structure like a dam and you need low heat of hydration, or if you have to transport the material to the very far job site, then that's something you want to look into that. You will have more time for finishes, but this could affect the earliest strength development and typically doesn't affect the final setting time. So really it's more looking at the initial setting time that we have talked about in the context of cement hydration. The opposite of retarders are accelerators. If you want to shorten the set time and accelerate early strength development, you use these admixtures, which are also useful in cold climates, for example, as here you see in the picture. This could be used. And there are some other admixtures. For example, you saw that in the beginning you can have shrinkage because of evaporation of water from very, very tiny pores. So you can use admixtures to minimize drawing shrinkage in the beginning. In concrete, there are some admixtures which help corrosion resistance. So they help mitigate corrosion of reinforcing steel in concrete. The last topic in cement is basically now mineral admixtures. This is different from what we talked about previously. These are supplementary cementitious materials, SCM. So this is when you don't use just Portland cement. So it is either added to Portland cement or ordinary Portland cement, or it is even replacing that. So it is being used to replace a percentage of cement weight, and the motivation is typically environmental impact, or it can be also better properties. And some of the important ones are fly ash, which, if you remember, we saw it in the video, slag, which is a byproduct of steel plant, or silica fume. And there are other types of admixtures. So these are powders pretty much. Previously, I told you that the products of cement hydration, the main product is CaCl, which actually carries the strength properties, and then we also have portlandite, which is soluble, and it doesn't have much of a strength properties. So you add, for example, pozzolans, which have silica or alumina, or both. So they are silicious or alumino-silicious materials that they are not cementitious by themselves, but when you add them, for example, to cement, they react with CH or CSH, and then they help improving strength and durability of concrete. So here you can see that these are two compounds in cement. So Pozzolanic reaction is basically, it releases hydrogen, which in cement hydration, so this is pretty much cement hydration, where you generate CSH and CH. Now if you add pozzolans here, like for example having silica, this is going to turn CH to CSH. CH doesn't improve strength, but this is something that we like CSH because that's the main glue in cement. And examples are silica fume, fly ash, and a slag. And the reaction is typically very slow. Some of these materials, they react directly with water, and they are called hydraulic. Some of them, they have to have CH and then some moisture, and they are called pozzolanic. And you can see that, for example, fly ash, there are two classes, F and C. Class F is typically more pozzolanic, and class C, it's more hydraulic. And silica fume is pretty much pozzolanic, meaning that it doesn't react directly with water. It needs to react with CH to actually create the useful CSH product. So fly ash we talked about, so we have two classes, and these are byproducts of coal, burning coal. Class F is from burning bituminous coal, class C sub-bituminous coal. So using it in concrete helps lowering the adverse environmental impact. And then slag, that is, we learned before that it's basically what you get at the bottom of blast furnace, and it can be used as cement replacement, so it's very useful. There are more details in the book if you're interested in. It's more important to understand the main concepts here. And finally, the water that you use to mix concrete, it's important that it has some minimum, it passes some minimum requirements. So if the total dissolved solids are less than 2000 ppm, everything is okay. If it is more, you need to test to make sure that this water is good enough as a mixed water. And it's typically very simple. You make samples with the questionable water. So here it becomes questionable. And you compare the compressive strengths of samples made with pure water and those made with questionable water. And if the difference is less than 90%, then you're okay. You also look at the setting time, and you want to make sure that the setting time between the mix made with the questionable water and pure water is not very different. So these are the important parts. Again, more details you can find in the book. So to wrap this up about cement, it's important to understand or remember how cement is produced. We looked at one video together in the class. There is another video you can look to get more information. The book also has more details. And it's important to know what are the 4 important chemical compounds in cement and what is the role of each one of them in cement hydration, heat release, and setting in terms of early strength development and rate of hydration. It's important to understand the porosity and the fact that porosity is affected by capillary pores, and there are also air voids in concrete which also reduce strength, etc., but they are not as important in the strength and permeability properties of concrete. Understand water to cement ratio, which is just the weight of water to the weight of cement, and see how it affects strength and permeability. We looked at some graphs together, so it's good to have that in mind. Explain basically these different admixtures that we discussed: air entraining agents, water reducers, retarders, and accelerators. Have an idea in what situations which one is being used. And it's important that you know some of the cement, the substitutive cementitious materials, and to know their functions and why they're being used. So some of the terms that you may want to look up to make sure that you can define them are cash, CSH, which is the main product of cement hydration, pozzolan, water to cement ratio, etc. Feel free to add to this list. Great, good luck.